right, so we've named and written formulas for some simple ionic compounds. We've added the transition metals and used the Roman numerals to note the charge. So now it's time to add the polyatomic ions. You probably recall polyatomic ions. They kind of look like little compounds, but they're not neutral. They have a charge. And we'll look at their structure, their kind of molecular structure when we do bonding to figure out why they have a charge. And it turns out that, in order to fill all the outer shells of these atoms in the polyatomic ion, we may need to gain or lose a few electrons, and that's what gives them their overall charge. These polyatomics are listed in a chart down at the bottom here, at least most of them. The ones that you'll come into contact are. And we do get the fun of memorizing them. Woohoo! It's never too soon to start. So have fun with that. And I'll give you a couple pointers in a second. But the more you use them, especially these common ones, you'll just kind of accidentally memorize them. It really is impressive. And some of the uncommon ones we can look up throughout the year. Writing formulas with polyatomic ions should be no different than writing any other binary formula. We'll still have a positive ion and a negative ion. We still need to acknowledge their charges. So here I've got some potassium carbonate. Potassium is always in the group on the periodic table that is +1. A lot of the polyatomics are going to end with ATE. Not all of them, but many do. So if I see that ending ATE, that's usually a good giveaway that it's a polyatomic instead of it just being like, oxide, regular oxygen off the periodic table. So for now, as I'm starting to kind of refresh my memory on the polyatomics, you may find yourself looking them up on this chart, which is totally fine. So I see my friend carbonate. There he is. CO3 with a charge of 2- or -2. Either is totally fine. So I look up the charges, and then I just have to make it neutral. So there really is still just one positive ion, one negative ion. We still have to make it neutral. Let's take 2 potassium. Okay, 2, and then carbonate was CO3. Done. That should be neutral. I should have a +2, -2. And again, you don't have to show work for these formulas. And eventually, I'm hoping that you don't need to do any work. You just write them in your head and then write them on paper. But for now, if it helps to write the charges in, go crazy. Tin 4 chromate. So again, I noticed that there's an ATE ending, which kind of makes me think it's probably a polyatomic. For now, I may start looking them up. Chromate, down on the bottom. There she is. Tin's charge in this case is a +4. And chromate is a -2. I need to make this neutral. So we'll probably take 2 chromates. Take 2 of those. That gives me a +4, -4. And so if I needed to multiply chromate's charge by 2, I need 2 chromate in the compound. And here's where you might remember using those parentheses. I've got tin. I only need 1. And you don't have to write 1s in a formula. Chromate, CrO4. I need 2 groups of chromate. This entire group, CrO4, has a charge of 2- or -2. I need 2 of those groups. That's when you must use parentheses. And the 2 goes on the outside. If you don't put chromate in parentheses, it looks like CrO42. And we don't mean for there to be 42 oxygen. We actually mean for there to be 8 oxygen in the end. But that chromate's kind of a package deal. So if we need more than 1, we use the parentheses. Now with potassium carbonate, the parentheses are optional. You only need 1 group of carbonate. So you don't have to put parentheses in. If you're ever unsure and you did put the parentheses around carbonate, nobody's going to mark that wrong. So if you're in doubt, just throw parentheses around any polyatomic ion, and I promise you it'll be right. You just don't need the parentheses if there's only 1 group present in the formula. Vanadium 7 hydroxide. That sounds fun. Vanadium is a transition metal that can have lots of different charges. So it seems weird, but this is right. The vanadium's charge is +7. Hydroxide is a real common polyatomic. We will definitely make friends with hydroxide. OH -1. Hydroxide is a -1. So in order to make this neutral, we're going to need 7 of them. We'll multiply that by 7. So my formula becomes vanadium. And then I must put hydroxide in parentheses with the 7 on the outside. 7 groups of hydroxide. So hopefully writing formulas with polyatomics is something that you've done before, and this comes back to you relatively easy. I get it. For a while, it's going to be hard to get these polyatomics memorized, and it seems like kind of a daunting task. But you really do use them so often that the more you force yourself to look them up, especially the most common ones, you really do kind of start to memorize them. And you may find yourself using little note cards or something like that to kind of help as you go. On the flip side, let's say we want to name compounds with polyatomic ions. All the same rules apply, and often again, these polyatomics will be familiar to you, or you might see parentheses. Well, that's a dead giveaway that it's a polyatomic ion. So let's say I've got this zinc, and then there's this big crazy thing in parentheses. If I'm not familiar with that giant group, I'm probably going to look it up for now, until eventually I become familiar with the acetate ion, C2H3O2 with a charge of -1. Now with zinc, technically we're dealing with a transition metal. So this is some kind of zinc acetate. And since zinc is a transition metal, we're always thinking that we need that Roman numeral to show the charge. Zinc and silver are 2 transition metals that may or may not have a Roman numeral. Zinc is like 99% of the time +2. So if I wanted to, I could check that the acetate was -1. There are 2 groups. Oh yeah. +2. So the zinc is +2. Optional. If you're ever unsure, I should say, throw it in there. But 99% of the time, the zinc will be +2. So if you ever are seeing a formula or a name and they don't give you a charge on zinc, you're safe assuming 2. With silver, it's almost always +1. The second group, NH4 is a real common polyatomic. It's probably one of the only positive ones that we'll deal with. Ammonium. I've got the ammonium ion. It only has 1 charge. It's only +2, so we're not going to worry about any kind of Roman numerals. And then again, another reason why I do want to memorize these polyatomics or become very familiar with them is so that I don't make a rookie mistake and name this something goofy like nitrogen, hydrogen, phosphorus oxide or something goofy. No, I want to recognize that group NH4 is ammonium. That group PO4, that's phosphate. Phosphate. There, that's an H. That looks a little better. And the last one listed, sodium. Well, that's probably my positive, my cation ion. And I never need Roman numerals with sodium. It's always +1. CO3. CO3 is a pretty common polyatomic. We mentioned him before, this carbonate group down here. We've got a hydrogen tucked in there. So brilliantly, this can be called sodium hydrogen carbonate. Hydrogen carbonate. Wow, look at that. Or hydrogen carbonate is commonly known as bicarbonate. So either would be fine. Carbonate. Sodium bicarbonate, baking soda. So it's totally fine either way, hydrogen carbonate or bicarbonate. Full credit, either option. Notice one thing. Carbonate had a charge of -2. Usually hydrogen has a charge of +1. So when you throw hydrogen in with this carbonate, the charge makes sense. Regular carbonate -2, hydrogen carbonate -1. It's like the carbonate -2 bonded to a hydrogen +1. This will happen a couple times. So, here's this chart and it looks giant and huge and intimidating. There's tons of polyatomics that I think I have to memorize. But there's actually a couple that kind of go together. Like, check out sulfate and hydrogen sulfate. Sulfate -2, hydrogen sulfate -1. Well, hydrogen's +1. And again, this could also be called bisulfate. Sometimes this kind of bothers people because they think that prefix bi should mean 2. In chemistry, bi means hydrogen. I know that's kind of awkward and confusing, but it does refer to a hydrogen. Or look what happens down here with phosphate. Phosphate is normally -3. Hydrogen phosphate is -2. Then there's a dihydrogen phosphate ion with a charge of -1. It makes sense. If each hydrogen is +1, the original charge goes from -3, -2, -1. So yeah, there's a whole bunch of polyatomics listed on this chart, but some of them we can kind of lump together. Another thing that we should mention, tips on memorizing some of these guys. There are some polyatomics that are really common. They're very stable. They're the ones we use most often in the lab. So things like ammonium. I would definitely know ammonium. Nitrate. We use nitrates all the time in the lab. Phosphate. There he is. We use phosphate quite a bit. Sulfate. Sulfates are real common. Carbonates are real common. Even this guy here, chlorate. Chlorate's pretty common. So a lot of these guys end in ATE, and these may be ones that you used in first year chem, and maybe you even memorized a few of them in first year chem. The most common usually ends with ATE. It's the most stable form of that particular polyatomic. If you take off one oxygen, the ending changes from ATE to ITE. So we go 8 to ite. So for example, nitrate is the most common, the most stable. One less oxygen turns it into nitrite. The charge stays the same. The difference is just NO3 versus NO2. Same thing happens with sulfate. Sulfate, most common, most stable. You take off one oxygen, sulfite, SO3 -2. Oh. Now the other form that we should be aware of, we should make note of this. What if I have just regular nitrogen -3? Now that's nitride. So my options, that's a goofy looking eye. There it is. IDE is the regular element of the periodic table. Sulfur -2 is sulfide. The most common, most stable polyatomic will end in ATE. One less oxygen goes to ITE. So the same thing kind of happens over here with my buddy chlorate. Chlorate is ClO3 -1. If I lose one oxygen, I go chlorite, ClO2 -1. The charge stays the same. Now, with the chlorites and chlorates, there are a few options listed here. If you have one less oxygen, the ending just changes from ATE to ITE. If you have two less, then we go hypo. and then we end ITE. Hypo means low. So this is one less oxygen. Actually, it's kind of two less oxygen than the original. Hypochlorite. The other option, what if we have an extra oxygen? So chlorate is the most stable, most common, ClO3 minus 1. If you have an extra oxygen, the ending stays ATE, but you'll see this PER, perchlorate prefix. So there might be kind of a good combo, these chlorates. That's really your only options. The most common, most stable ends in ATE. One less oxygen changes the ending to ITE. Two less, we go hypo and then ITE. If we add an oxygen, we go perchlorate. Ending stays ATE. Now again, there's other polyatomics on this list. There's thiocyanate, which can also be written as SCN minus 1. You might see it written that way. Either is totally acceptable. Acetate is very common. Permanganate. There's a couple chromate ions. Peroxide is O2 minus 2. The oxalate ion is another one that we'll use maybe once throughout the year. So, I mean, it's not as big of a task as it might look if you kind of break them down into groups. And really, there are some of these polyatomics that we might only use once or twice. And in that case, we'll look it up. But some of these common ones, we will definitely need to recognize their formulas and their charges.